Hey everyone, this was a really good question thread, so I just wanted to post a reply here, and I thought it would work really well with figures, so I wanted to make a video for it, okay? So one of the questions most directly was about comparing water with ammonia in terms of boiling point, and you guys can look these up on the internet pretty easily and see that water does indeed have a higher boiling point. So the question was, well, I only have 2 hydrogens here on water, but I have 1, 2, 3 on ammonia. So why is that? Okay, so I wanted to take a second to explain this. So the number of hydrogens is important, but the most important factor is the strength, is the strength of this bond here in terms of the difference in electronegativity. Okay, let's just take a second to pick apart the anatomy of a hydrogen bond real quick. Obviously, hydrogen's a key player, as I mentioned. We actually call this one the species with the hydrogen. This is the donor, the hydrogen bond donor. And then the other one would be the acceptor. And of course, it's the connection between that donor hydrogen and that acceptor lone pair. That's that hydrogen bond, right? When I'm referring to a hydrogen bond, that's what I'm talking about, is that connection there. So the difference in electronegativity between, in this case, the oxygen and the hydrogen are so important because remember that difference in electronegativity, that bond polarity, will mean that there's a partial negative end on that oxygen atom and a partial positive end on that hydrogen, right? So that bond polarity increases the strength of the hydrogen bond because I have the same thing down on this molecule here. That oxygen has a partial negative charge, pulling electron density away from that hydrogen. That hydrogen has a partial positive, right? So that's why when you're talking about hydrogen bonding, the strength of that hydrogen bond is first dependent on the difference in electronegativity between whoever's bound to the hydrogen, in this case, oxygen. Right, so this is just a more electronegative, a higher electronegative difference in electronegativity between oxygen and hydrogen than you get over here between nitrogen and hydrogen. So this, I don't know how I can do that, maybe just make it smaller. So this, I still have a partial negative on the nitrogen and a partial positive on the hydrogen. Same thing over here. But it's just not as much as with the oxygen and the hydrogen as with water, okay? So there certainly is a hydrogen bond there. It's just not as strong because the difference in electronegativity isn't as great, okay? Now there was another thing that was mentioned that's even that much more, and that is the fact that, I'm gonna erase some of my doodling here. Okay. Each water molecule, not only does it have 2 donors, but it also has 2 acceptor sites as well, right here as well. So 2 hydrogens that can be donors as well as 2 lone pairs that can be acceptors, which is why each water molecule can, in theory, coordinate with 4 different water molecules at one time, okay? With ammonia, it does not have that same ability. It can only connect with 2, right? Because it only, although it has 3 donors, it only has 1 acceptor, so it can at most coordinate with 2 different molecules. So it was correct that the fact that oxygen has 2 lone pairs and thus can make up to 4 hydrogen bonds at one time is part of the reason that that water is particularly good at, or actually has a particularly high boiling point for how small of a compound it is. Water is a little bizarre in that it is very, very tiny, but still a liquid at room temperature. And it has everything to do with how strongly it interacts with its neighbors. That's why water is the quintessential polar solvent. The other just like fun fact, it can of course make 4 at one time, but remember that we're talking about things in the liquid state. These things are tumbling around. They're never just like frozen in place, okay? So these hydrogen bonds are being made and broken all the time. That said, it turns out that if you could like freeze time and take a look at the average number of hydrogen bonds being made, it's around like around 3.8 of the 4 possible ones at any given time, which is an incredible amount of structure for that liquid to have. So that's another thing that makes water a little bizarre. All right, so when we're talking about the number of hydrogen bonds, that's really going to come into play in terms of determining which one has stronger intermolecular forces when we're comparing two compounds where their hydrogen bond has the same difference in electronegativity. So this guy over here, this is what we call a primary amine, and we'll get into what that all means, but I think hearing the language is going to be important for it starting to sound normal. So this is what we call a primary amine. And this has 2 donors, right? 2 of those hydrogens, nitrogen-hydrogen bonds that can be a donor for a hydrogen bond. And 1 acceptor, 1 lone pair. 1 acceptor. This compound over here is what we call a secondary amine. And it only has 1 donor, right? There's only 1 nitrogen-hydrogen bond, as well as 1 acceptor. So in this case, this one, we would expect to have the higher BP, higher boiling point. So why is that? That has to do with, again, the fact that there are just more hydrogens that can participate in hydrogen bonding. Okay, now if you're clever, you're gonna say, well, if you can only form one, bond with 1 donor and 1 acceptor at a time, both those sites are occupied, then why would it matter to have 2 donors? Why would that be such a boost? Well, because again, these things are all fleeting, right? They're only temporary. So it's kind of a numbers game. These molecules are bumping into each other randomly. The more different positions that you're going to form that nice, strong hydrogen bond, the better, right? So it's just sort of a numbers game. Things are more likely to happen if you have more donors, even if there is just 1 acceptor. So that is why this explanation of having more hydrogen bonds, having more hydrogens to hydrogen bond will help, right? All right, so the last one I want to talk about is when size is a factor here. Okay, so let's take 2 compounds, for example, chlorine gas and bromine, right? So you might remember back from your general chemistry that at room temperature, this is a gas and this is a liquid, right? So which one has the stronger intermolecular forces? Knowing what we learned, you should hopefully be able to answer that. So take a moment if you need to pause and see. So the fact that bromine's a liquid means that this one has stronger intermolecular forces. So why is that? Okay, so they're both, right? If we take just a look at these compounds here, in terms of their Lewis structure, this is what we got, right? Same sort of looking compounds, single bonded to one another, 3 lone pairs. Both of them are very electronegative atoms, but nonetheless, these are non-polar bonds because, you got the same thing on either side. Nobody can pull electrons any better. So these are both non-polar. So what's the difference between these two? The biggest difference is size. The size of a chlorine atom. So if I'm just going to sort of draw this electron cloud in, it's going to look something like that. Well, bromine's much larger, right? That was terrible. Assume that those are the same size, but nonetheless, you get the idea. A bromine molecule or a liquid bromine Br2 molecule is just much bigger than a chlorine molecule. So why does that matter? Well, if you're larger in terms of radius, that means that you're also larger in terms of surface area. And remember, surface area is one buzzword that you should have connected with one particular intermolecular force, especially important in nonpolar compounds, and that is London dispersion forces, right? So the fact that this has more, that was terrible, more surface area is why it's going to have stronger intermolecular forces and thus is a liquid at room temperature as opposed to a gas. Okay, so these were some things that were touched on in the question discussion, which was awesome, and so I just wanted to sort of clarify in terms of some very well drawn pictures why that would be.